Okay, so in this video we're going to be talking about the center of mass. And what is the center of mass, do you ask? Well, it's basically what the name implies. It's the center of where all the mass is located. Like basically, if you took out all the mass in an object, flattened it out so it would be all uniformly distributed, it would be dead in the center. And then if we were to put that object back together again, it would still be that center. I mean, that's how I see it, but let me give you some examples so you would actually understand conceptually and visually. So let's assume we had a square, okay? And ignore this formula for a second. I'm going to get to that in a moment. Alright, so let's say we had a square of length, Yeah, let's say we had a square of length 5. Okay? Where is the center of mass located if the mass is already uniformly distributed? And what are the coordinates of that? Okay, so to find coordinates of center of mass, we always have to use a reference point. We could use this corner as a reference point, we could use this point as a reference point, this point as a or even the center we could use as a reference point. You have to make sure that you clarify where your center point is when you're given the center of mass, or if the problem, if you ever run across this then typically the reference point is given to you in the problem. But let's go ahead and use this corner as a reference point because I don't like using negatives that often. So we had the point 0, 0, and that's our reference point. So that means that this whole square is in the first quadrant. So this point would be 5, 0, 0, 5. This would be 5, 0. And then this would be 5, 5. Okay. And then obviously because our square is uniformly distributed, the center of mass would be right in the center, right? And we would know if the center of mass is deadly in the center is if either they tell you it's evenly distributed, or the mass of every single particle, like the particle over here, the particle over here, the particle over here, 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 and so on and so forth, is all even. So we will know it's dead in the center, and the coordinates of that in this case, we would go halfway through the x, so it would be 2.5 here, and then halfway through the y, so 2.5 here. So the coordinates would be 2.5, 2.5. And remember, our coordinates is all relative, so it would be 2.5 to the left, or not to the left, to the right, and 2.5 up. So you're probably continuously looking to this equation, probably wondering, okay, how does he get that equation? Simple. Alright, and I'm going to show you an example that involves this equation, but this is an equation to find the x-coordinate of any center of mass. The y-coordinate is exactly the same thing, except you replace all the x's with y's. So what it is that you take the mass of every point and the relative coordinate of the x or y of every single point, and then find the sum of those products, and then divide it by the sum of all the masses of every single point that you used. So let's say we use just these 2 points right here. And let's say they're mass m. No, that's a bad m. They're each of mass m. So from using this equation right here, we would have to have m times 0, because its x-coordinate is 0, plus m times 5, because its m-coordinate is 5. And then if we had more points, like let's add in 2 more. We know these two are m's. Its x-coordinate is 5, so we would have plus 5m, or m5, because m, and then x-coordinate is 5. And then the x-coordinate here is 0, so 5, or 0, and then, so m0. So we have 2 zeros, 2 5s, so our numerator would end up being 5 or no, not 5, then being 10m divided by the sum. There's 4m, so 4m. Cancel those out. So we would have 2.5 as our x-coordinate, right? Same thing with the y-coordinate. If we did the same exact thing, because there were 2 points of the 4 that we used that have 5 as their y, and 2 points that have 0 as their y, it would come up to the same exact thing. Try it out on your own if you don't believe me, but it would turn out to be the same exact thing. We could add in additional points if we wanted to. The result would still be the same. Remember to always use relative coordinates, though. So as long as it's uniformly distributed, the center of mass would always be right here in the dead center. And let's give an example where we only have one dimension to deal with, so just the x dimension this time. Alright, so let's say we had a rod of length L. I did the wrong way, didn't I? Of length L. And we are going to use, let's go ahead and use 4 points again. We could use 2, but it doesn't really matter. 1, 2, 3, 4. And they're all of mass m because this is uniformly distributed. Okay? And then this distance right here is L over 3. This distance over here is L over 3. This distance over here is L over 3. So they're all split into thirds, basically. Where is the center of mass? We're going to go ahead and use this point as 0, 0. Alright? Now, we already know where the center of mass should be. It should be over here at L over 2, right? Okay, so let's apply our formula to figure out exactly where it's supposed to be, just to make sure it's L over 2. And then the y coordinate is 0, obviously, because there is no y direction, it's just purely x in this case. So, m1, x1, we'll use this as m1, it's 0, 0, so we'll cancel that out. We don't even need to consider it. m2 is at L over 3, so we'll write out m L over 3 plus the same thing, except it's 2L over 3 from the reference point. Remember, it's a distance from the reference point that we're dealing with right now. So it would be 2ml over 3 plus, and this m is all the way from over there, so it's L. So we'll just write ml, or we can just write 3ml over 3. And now, since we're dealing with 4, we found the coordinates of 4 points. I didn't write down this one because it's 0 ml over 3, which is equal to 0, so there's really no point. But we're still referencing this point, so we're using this point. Well, no, we're just using this point in our calculations. So this over here would have 4m. And if we didn't have this point to reference, then, and we're just using these 3 points with masses and all the other ones didn't have mass, the center of mass wouldn't be right here. It would actually be closer to over here if this particle didn't have a mass. And I'm going to show you what the result would be if this was actually 3m. Okay? So remember, in center of mass, it has to be evenly distributed. That's why when I did 4 points, they're evenly separated from each other. If they weren't evenly separated from each other, then the center of mass wouldn't be straight in the middle. I mean, that's the definition of evenly distributed. It has to be equal distance from each other. Anyway, so we would add all this up. We would get 6ml over 3, or 2ml. Yeah, it would be 2ml. over 4m. The m's would cancel out, so we would have L over 2. And that's what we had over here, right? That's what we had the first time. Now, if it wasn't 4m, and let's say we excluded this point, but we're still using this point as a reference point for 0, 0, we would have a 3 here, which means that this 4 over here would be a 3, which actually means that our distance is 2L over 3, or 2/3 L. That would mean that this point right here was the actual center of mass, which actually makes sense concerning these 3 points are the only mass points that we're referencing to. This mass, all 3 of them are exactly the same. This point is the same distance from this one as this one is the same distance from that one. And like, think of the arithmetic mean. Like, that's what this formula is basically based off of. Like, if you took the average of the distances that they are, you should get where the center of mass is. I mean, isn't that what I just basically said from saying, okay, these are all exactly the same, they're the exact same distance, so it has to be in the middle. Pretty much, right? And that's the same definition of uniform mass. This whole section right here would be negligible because there's no mass at any point on it from what we're saying. Okay? So if we just had 3 particles in space, you could figure out the center of mass of those. Now, there is one more thing to talk about. Center of gravity. The center of gravity is exactly the same as the center of mass, formula-wise, except instead of determining the weight of the mass of every single one, we're referring to the weight of every single one. So, going back to that rod example that we had, and saying that this whole thing was of length L, right? We have these 4 points here, which should all be equal distance. It doesn't look at equal distance. So L over 3, L over 3, L over 3. All of them are of mass m, evenly distributed. Okay, so if they're all of mass m, and if gravity is evenly distributed as well throughout the object, then the center of gravity would actually coincide with the center of mass. In the real world, that's not always true because of gravitational fields and the way gravity works and stuff, but mathematically, it's pretty much the same. There are times where they're not the same, and that goes into a whole other concept, which I'm not going to explain in this video. But just realize that if you want to find the center of gravity, it's the same exact formula. So let's use this as a reference point, like before, 0, 0. So then, if we were to use the same formula, we would have mg as our weight, mg as our weight, mg as our weight, mg as our... So basically, we took every point and multiplied by g. So instead of g, we'll use w for every single point. We'll donate mg equals w for weight. So then the x-coordinate here is 0. The weight of this point is w, but there's really no point to write it down. The weight of this point is w, and it's L3, or a third of L away. We would have w, so 2WL, it's the same exact thing as before. And then that's a whole L, but we're going to write it as 3WL. Makes it easier for you to see. And then there's 4 points that we're referencing to, so 4W. And then, so that would equal, the same as before, 6WL over 3, which equals 2WL over 4W. The w's cancel out, that reduces, so that equals L over 2. So the center of gravity in this case is exactly the same as the center of mass that we did in the previous example. Okay? So that's basically the concept behind center of mass and center of gravity. Now before we go, I want to show center of mass, center of gravity problem dealing with the same type of problem, but like with different distances and different masses. So let's say we had a vertical rod this time. Let's move it over here. Let's say we had a vertical rod, and then we're referencing this point here. Probably can't see it. This point here. This point here. This point here, and this point here. This distance is L over 6. This distance is L over 3. This distance is L over 2. Yeah, wrong tool. Okay. That equals, yeah, that should equal up fine. And then let's say this is a mass M. This is a mass 2M. This is a mass M, and this is also a mass of 2M. So, what do you think the center of mass is conceptually before we even get it? Well, considering these masses on the outside is smaller compared to these two, we can assume that the center of mass is probably going to be closer in between these two right here. It will be most likely closer. And then since the masses are closer to this side than they are to this side, and they are L2 apart, even though there would be somewhat in the middle of these two, it would probably be closer on the second half of L. So let's assume that this point right here is L over 2. And we're donating this point as 0, 0, right? Well, if that was L over 2, and remember this distance is L over 2, but right, I'm going to assume that, let's go ahead and move that point then. Let's move it like closer over here. Yeah, I like it right here. So then L over 2. And then this point is 0, 0. Okay, so let's go ahead and figure out what the center of mass and center of gravity is. So first, the center of mass. Since we're just dealing with the y, we use the formula for y. If we were dealing with x as well, then we'll do both, but in this case we only have to deal with the y. So, first off, we have this point right here. It's at 0 as its y-coordinate, so it would actually be 0 in the equation, so we don't even need to write it. 2m is located at L over 6, so then we basically write ml over 3. Because it is 2m times L over 6, which reduces to that. Alright? L over 2 is, not L over 2. This point, 2m, is located from L over 2 plus L over 6, which is 2/3 away, from 2/3 L from here. So then we would have 4ml over 3. This one is a whole L from over here, so then we write 3ml. Because from what it looks like, our denominators are all 3, and I just want to show you how it all adds up. Now we add up all the masses, 1, 2, 3, 4, 5, 6, 6m. That's a bad M. Alright, so now we have ml over 3 plus 4ml over 3 plus 3ml over 3, which should add up to 8ml over 3. 8ml over 3 divided by 6m, which we can just write in the denominator here. So then the m's would cancel out. This reduced to a 3, and this reduces to a 4. So our center of mass in this case is located at the y coordinate 4L over 9. Which, as we predicted, is going to be slightly less than L over 2. And that's what it is. Slightly less than L over 2 because these two masses, it should be somewhere in between them. However, because these two are like shifted closer to this point than this point, then it should be closer on this half of the board. So 4L over 9. If we were to do the same thing and change every single thing to W, because G in this case is evenly distributed, which in math problems you practically assume that is evenly distributed. So we have W, 2W, you basically replace M with W. Then you should get the same answer for the center of gravity. Okay? Well, that's all I have for this video. So, see you in another one.